Today we're going to be working on section 4.6, part 1, and we're going to specifically be working with exponential growth word problems. And in the next class, we'll look at the second part of this section and work with exponential decay problems. Okay, so I have these 5 problems as a startup to review some of the different types of solving equations that we did in the last class. So there's some exponential equations and some logarithmic equations for you to practice with. So pause this video and try these and then check your answers. Okay, on the first one here, we have like bases. So with the like bases, we can just set the exponents equal. Okay, we have a quadratic here. So what I'm going to do is I'm going to pull everything over to one side. And I need to factor this because it's a quadratic. So it will factor x minus 2, x minus 1. So I'll set each factor equal to 0. So I'm going to get 2 and 1 as my answers. Okay, the next one, I have a logarithmic equation. So the first thing we want to do is isolate the logarithm. So I'll need to divide both sides by 5. Okay, if you remember our strategy when we have a logarithm on one side and not the other is to put it in exponential form. So we have an understood base of e. So it's going to be e to the 4/5 power equals 3 minus x. So we're just going to circle around here. Okay, x is the variable we're solving for, so we want to move the 3. And then we'll divide by -1. So x is going to be negative e to the negative 4/5 plus 3, because we're just changing the signs. Or if we want to write it like this, then that's acceptable as well. So our next one here, we actually have logs on both sides. So we want to condense or combine these two together into one logarithm. So we're going to have the log, and we're going to multiply these two together here. Okay, because we have logs with the same base on both sides, we're just going to be left with this. So I'll distribute here. Subtract our 2x because this is just a linear equation. I'll divide by 3, and so x is going to be 2/3. Okay, next one, we have an exponential equation, so we want to isolate the exponential function here. First thing we're going to do is subtract 10 from both sides. Okay, next we're going to divide away the 2. And we know that to get this exponent to come down in front, we've got to take the log of both sides. So by our properties, this will come down in front. Okay, we're going to divide away the log of 3. So I've got x plus 1 equals log of 45 divided by the log of 3. So I'm going to subtract 1. So my final answer is going to be x equals the log of 45 divided by the log of 3 minus 1. And if, depending on the instructions on WebAssign, you can go ahead and put this in your calculator and get a decimal answer, or you can leave it like this if it's asking for an exact answer. Okay, next we have another exponential function. So I'm going to divide away the 2. Okay, we need to get rid of this base here and bring this down in front. So I'm going to take the natural log. Okay, natural log and e cancel. Divide by 12. So x is going to be the natural log of 17 halves over 12 for an exact answer. Okay, and so you can double check these here if you want to have it paused for longer. One thing I didn't mention on this, on letter D, if you have an answer like this, that's also equivalent to this. Okay, so moving into section 4.6 today, modeling with exponential functions. Like I said, we're going to be looking at the growth functions today. Okay, so we've already talked about there's lots of types of practical applications of exponential functions, including population growth, virus growth, decay, heat diffusion, and lots of others. So we're going to be looking at several of these today. So what I have gone over to here is a website, electionprinceton.edu, and it's talking about the doubling times of COVID in different parts of the country. So if we look at this, there's actually a chart near the bottom here where you can look at the different states and look at their doubling times and compare it to last week. So for instance, if we wanted to look at North Carolina is actually down here. So basically it's doubling. We're going to be talking a lot about doubling time today, but essentially the rate, and this is talking about, go back up to the top here where we can see the context of this a little bit. This is actually talking about the doubling time of the coronavirus deaths during the pandemic. So if you look at this chart here, in this column, we're going to be looking at what it's currently doing. In this last column, we're going to be looking at last week. So if we look down here at North Carolina, basically our current week, we're at, our death total is going to double every 204 days. And as of last week, our doubling time was 192.7 days. So you can see that it's doubling for North Carolina a little bit slower than it was a week ago. So you can kind of compare here and see like which states have the lower doubling time actually means it's growing the fastest, because the quicker it doubles, the faster it's growing. So so that's just kind of letting you see how doubling times relate to the current situation that we're in today. So just to talk a little bit more about doubling time, this is talking about bacteria. Viruses are going to work basically the same way with this. So the bacteria, this particular bacteria divides every hour. So we'll go from 1, we'll start with 1 at the first, at time t equals 0, which is our first hour, or at the start. So after 1 hour, it's divided one time and we're at 2. It'll divide again and we'll be at 4, and so forth. So you can see how quickly something will grow when it is doubling. And so when we look at the model for that, this base here is a 2 because we are doubling. If we were tripling every hour, then this would be a 3. If we were like dividing in half every hour, then this would be a 1/2. So whatever this base is an indication of the multiplier that we're using in the exponential model there. Okay, so on this one, we're going to look specifically at exponential growth with doubling times. So it's important to understand your notation on these. This is indicating the amount that you're going to have after a time t. N with a subscript 0, anything with a little subscript 0 is going to be your initial or starting value. T is going to be time, and in this model, A is going to be the amount of time it takes to double. The main thing is that you need to remember that A and T have to be the same units. So these two have to be in the same units. They could be in minutes, they could be in hours, days, months, years, whatever. They just have to both be the same. So keep that in mind as we go through this. Okay, so here we have a problem. Under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. So this is our starting value. So this is going to be our N sub 0. We know that it doubles, so we're going to have our base being 2. And the amount of time it takes to double is every 3 hours. So what it's given me there is our A. Okay, so it's asking us to find a model, or basically an equation. So we're going to use the model N of t equals N sub 0 times 2, because we're doubling, to the T over A. So that was the model that you had here that we were working with. It's also on your formula sheet, so if you'll make sure that you have that for your quizzes and tests, I think you'll find that it's going to be helpful. So to fill in the model, we're going to leave the N of T where it's at. We're going to replace the starting value with 1,000. It's doubling, so we're going to use a base of 2. T is our variable, and A is our doubling time, so that's going to be our 3. So this is going to be our model that represents the bacteria population after T hours. So part B, how many bacteria are in the colony after 15 hours? So we're just going to find 15, plug 15 in. That's 1,000 times 2 to the 5th power, which is going to be 32,000. After how many hours will the bacteria count reach 100,000? Okay, so going back to this model that we found here, okay, so using this model here, we're asked to find how many hours. So we're asked to find T. So after how many hours will the bacteria count reach 100,000? So this is the amount of bacteria after a certain number of hours. So this is going to represent our N of T. This is going to go here, and we're going to be asked to find the T. So when I set this up, I'm going to put 100,000 in the place of this N of T equals 100 times 2 to the T over 3. And this is why we spent like the last 2 days solving these equations, is because we can set it up, but then you're going to have to solve the same type equations that you've been doing. So if I divide both sides by 1,000, which would be the first thing I would need to do, then what's going to happen is I'm going to end up with 100 equals 2 to the T over 3. We'll need to take the log of both sides in order to get this variable down. And I'm going to be tight on room here, but I'm going to try to make it work. Okay, so here I'm going to have log of 100, and I'm going to bring this T over 3 down. Okay, I want to get rid of the 3 as a denominator, so I'm actually going to multiply both sides by 3. And then the last thing I'm going to do is divide by the log of 2. So I'm going to come back up here, and I'm going to have T equals 3 log of 100 divided by the log of 2. And since this is a word problem, we're going to go ahead and give an approximation for that. And that approximation is going to be 19.93. And our units on this is hours. Okay. So this particular bacteria that doubled every 3 hours started with 1,000 bacteria. And after a little less than 20 hours, it was already up to 100,000 bacteria. Okay, the next type of growth we're going to look at is when you're given relative growth rate. So with relative growth rate, you're going to use this formula. Again, you're going to have the N of T is the amount after a time T. N sub 0 is going to be your initial starting amount. The R is your relative growth rate, and your T is going to be your time. Okay, so we have this problem that we're going to work with here. And if you feel comfortable and want to go ahead and try the different parts of the problem, then by all means go ahead. If not, then you can see what I do with this. The first one, the initial bacteria count in a culture is 500, so that's my N sub 0. A biologist later makes a sample count of bacteria in the culture and finds that the relative growth rate, which is my R, is 40% per hour. So I'm going to put 0.04. Sorry, 0.40 for my rate. Okay. So we want to find a function that models the number of bacteria after T hours. So I'm going to reference my model here and just write that down. It's very much like the PERT equation. So we've got n of t equals n sub 0 e to the RT. So since we're asked for a model, we're going to leave the n of t here. We're going to substitute in the initial amount. We're going to put the R in for the rate. And then we're going to leave the t as part of our model. So this is going to be the model for this scenario that they have described for us here. Okay, so what is the estimated count after t hours? We're just going to use that equation that we just found, and we're going to plug in for 10 hours. So when we put all this in the calculator, we're going to get that that's approximately 27,300. And I think that actually comes out to be like 27,299. But generally, when we're talking about that large of numbers, we'll just go ahead and round it to 27,300. Okay, part C. After how many hours will the bacteria count reach 80,000? So again, we'll go back to our model that we found. Okay. And we want to know after how many hours, so we're finding T, will the bacteria count reach 80,000? So 80,000 is going to be our N of T. So we're going to have 80,000 equals 500 e to the 0.4 t. Okay, so now once we've got this, then it becomes a problem just like in section 4.5. We've got to get our exponential function by itself, so I'm going to divide by the 500. Okay, so 80,000 divided by 500 is 160. Okay, you know that when we solve an exponential equation with a base of e, we need to use the natural logarithm. Okay, and when we do that, these cancel. We'll need to divide by the 0.4. So t is going to be approximately, if I divide the natural log of 160 divided by 0.4, t is approximately 12.68. And this is talking again about hours. So in 12.68 hours, our bacteria culture will have grown from 500 to 80,000 bacteria. Okay, sketch the graph. In this section, I'm not really concerned about detailed graphs. Obviously, you can do these on your calculator. One thing to notice is that if I have this as my model, then this is actually my y-intercept. So obviously, you're going to need a window much larger than the standard -10 to 10 for your x-min, x-max, and so forth. So you're going to have to play around with it a little bit, but you automatically know what your y-intercept is, so it's going to have to be at least 500. This particular graph is showing it all the way up to 5,000, so you can kind of play around with it a little bit and see what you need your window to be on that. Okay, here we've got an example dealing with a rabbit population. So a certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100, and it's doubling every 3 months. So what was the initial size of the rabbit population? When we look at this particular example, they are not giving us a starting value. So we've actually got to go in and figure out what the starting value would be. So we're going to go to the model, the n of t equals n sub 0 times 2 to the t over a. Okay, and we're going to figure out what we know of this. Okay, we know that currently there are 4,100 rabbits on the island. Okay, so basically what we're saying is we don't really know what we started with, but after 8 months, we have 4,100 rabbits. So for time 8, the number of rabbits is 4,100. Okay, so 4,100 is our N of 8. So this is the amount after a given time. So the amount after 8 months is 4,100. We don't know our starting value. We know the time because it's 8 months that has elapsed, and it doubles every 3 months. So we put 3 in for the A. And then from here, this is just basically dividing by this number. So I'm going to divide by 2 to the 8/3. So I'm going to get that N sub 0 is 646. So my model then is going to be my starting value, which is 646, and it's a doubling problem, and it doubles every 3 months. So we're going to have this as our model. Notice that when I put in the 8 here, these two units had to match up. So we're talking about 8 months and 3 months, so they do have to be the same there. Okay, estimate the population 1 year after the rabbits were introduced to the island. Okay, so we're going to go back to our model. We said it was 646 times 2 to the t over 3. So 1 year after the rabbits were introduced to the island, we need it to be in months instead of years. So this is going to be the same thing as 12 months. So I'm going to do 646 plug in the 12 for the time. That's how much time has elapsed. Okay, so when I do that, I'm going to have 646 times 2 to the 4th, which is 10,336. So that is the amount of rabbits that we have after 1 year. Okay, so we started with 646, and at the end of a year, those 646 rabbits had become 10,336 rabbits. As far as sketching the graph, you could obviously put this in your calculator, and you would see that you have a exponential growth function that looks like this. Okay, so that takes us to the end of today's lesson.